Hello everyone, and welcome to the second MDPI webinar on water, which is entitled Climate Change Impact on the World Oceans and Coastal Systems, Proofing, Adapting, Mitigating. Thank you very much for joining us today. This is the second webinar of this series based on the special issues and sections from our water journal. If you are interested in submitting your paper to a special issue, a list of all the open ones is available on the webinar webpage. This webinar will be chaired by Professor Marcel Stive from Delft University, and we'll have three presentations given by Dr. Sam Dupont, Dr. Georg Ungiser, and Dr. Kevin Xu. This will be followed by a discussion and a Q&A session moderated by Professor Stive and myself. If you have any questions, please feel free to post them in the Q&A box. I would also like to remind everyone that this webinar is being recorded and that we will also have a YouTube live streaming today. The recording will be posted on the webinar webpage as soon as possible for everyone to watch it. So finally, just to present our chair, Professor Marcel Stive is an emeritus professor of the Coastal Engineering Chair at Delft University of Technology, and he has 40 years of experience in research and consultancy projects in the fields of hydraulic engineering, coastal morphodynamics, coastal biogeomorphology, and coastal and estuary management. In 2012, he received an honorary doctorate from Lund University in Sweden. In 2013, he was knighted in the Order of the Dutch Lion, and between 2014 and 2018, he received the Coastal Sediment Award, the ASSI Coastal Award, and the Jiangsu Province Friendship Award. I will hand out the microphone to him now. Thank you, Marcel, for accepting to chair this webinar, and everyone enjoy.
And welcome, everyone. Either good morning, good afternoon, good evening, or good night, wherever you are. We are very honored that you will join our seminar, our webinar. And we have three fantastic speakers on the topic of the impact of climate change on the world's oceans and coastal systems. Of course, climate variations have always impacted our ocean and coastal systems. But a global concern is that the near future rate of climate change may reach levels of which the impact is beyond our capacity to respond. And so the big question is it possible to make our oceans and coasts climate proof? Or if not, can we achieve successful adaptation and mitigation? These are the aspects we'll try to address. And of course, it is a bit focused on specific areas and regions. Well, I already welcomed you, and once again, thank you for your interest. We have three very good speakers. Sam Dupont from Sweden on the impact of ocean acidification and warming due to climate change on marine ecosystems. We have Georg Ungiser on Venice lagoon response to sea level rise and climate change. And in a similar sense, Kevin Xu on the Mississippi Delta response to sea level rise and climate change. Now, Venice Lagoon and the Mississippi Delta are, of course, very important examples where both human impacts and climate change come together. The importance of the ocean in the world system of climate, etc., is, of course, beyond discussion. Sam is an associate professor in Sweden, and so he will talk about oceans and what happens there and how it impacts on marine ecosystems. Georg is director of research of the famous Institute of Marine Sciences in Venice, Italy, and his research is centered around the Venice Lagoon. Kevin Xu is interim director of the Coastal Studies Institute and a distinguished professor in the Department of Oceanography and Coastal Sciences at LSU. His research is focused on all the things that happen in the Mississippi Delta. Now, we chose a title that is maybe a bit challenging, Proving, Adapting and Mitigating. Proving is a very difficult issue. Some people doubt if you can make coasts and oceans climate proof. When we talk about coasts, there are examples where coastal barriers, despite sea level rise, have rolled seaward, and where coastal reefs have been able to grow with sea level rise. But all this was under sea level rise rates of the late Holocene. And in the Anthropocene, we will see an increase of sea level rise, and it may be impossible to even think about proving. And so it is most probable that adaptation and mitigations are our best options. In a very simplistic way, but it always helps to simplify things, you may say that the strategies, here we look at a very simplistic picture, right? This is just in the cross-shore direction, and the reality is much more complex. But you could say, if we look at the simplified form, we can say we have options like retreat, accommodate, protect. That's all in a mitigation adaptation realm. And then there's a difference between urbanized regions, which is the top three, wetlands, and where agriculture and aquaculture are done near the coast. Reality is, however, more complex, and the three speakers will show you that. Think of geographic three-dimensionality. Think of the impact of the ocean and how it impacts on our climate, on wave energy and storm surges and hurricanes. Think of human interventions that we'll see in the deltas of Venice and the Mississippi. Think of composed systems. So let me now give the word to the first speaker, Dr. Sam Dupont. He will talk about ocean acidification and warming and other aspects on the ecosystems, the marine ecosystems. Thank you.
All right, thank you very much. Is that working well? Can everybody see the...
Yeah, it's perfect.
Awesome. Fantastic. So thanks for the invitation, for giving me the opportunity to say a few words during this webinar. So because I'm the first speaker here, I decided to maybe start a bit by stepping back a little bit and remind us how important the ocean is for us. So basically, without the ocean, there would be no life on Earth. The ocean is providing us with countless services, from the air we breathe, the compound that you can find into the ocean that help us to stay healthy, seafood that is a major source of protein for many people. It has cultural aspect. The biodiversity in the ocean is also unique in many ways, and also coastal protection and so on. And also one of the most important services that the ocean is providing us is providing a feedback with the climate. So without the ocean, the climate would be much worse than it is today. The thing is that we depend on the ocean, and the ocean is already under threat because of all the human activities. And there's many ways of quantifying that. And one is called the Ocean Health Index. And I've put a lot of reference in the presentation, so you can later go and have a look if you're interested into the details. But that's basically a metric identifying what is the situation today. And it's between 0 and 100, 100 being a perfectly healthy ocean. And overall, when you do that today, the ocean is healthy at 60%, which is not great. But what you can see on the map is that it really depends on where you are. In some countries, the situation is much better. So I'm from Sweden, and the situation here is not too bad. But if you go in some countries, and in particular in developing countries, the situation can be really dire today. And we really depend on a healthy ocean to be healthy ourselves. So that's really, really important that we do our best to limit the negative consequences we have on the ocean. The thing is that we have such a consequence on the ocean because we are in a growing world. So there is a growing demography. We are now more than 7 billion people on the planet. And because of this crazy amount of people we are putting a lot of pressure on the ocean. And that's a different scale from global to local. So we produce toxicants that are released in the ocean, more than 100,000 today. And then we have more global things like global warming, deoxygenation, ocean acidification, but all that together put a lot of pressure on the ocean with consequences for us. And the one I'm going to talk a little bit more about today is carbon dioxide. So as you know, because of human activities, we release a lot of carbon dioxide into the atmosphere, and that's through burning fossil fuel and deforestation. And this is the classic graph when you see the increase in carbon dioxide emission through time since the beginning of the Industrial Revolution. You see you have this huge increase. And what you can also see is that every time there is a big human activity that can influence this, like a war or a financial crisis or now the coronavirus, there is a decrease in carbon dioxide emissions. So that shows clearly that we are responsible for this. We are producing this carbon dioxide that is released into the atmosphere, and that has tons of negative consequences. So that's climate change. So you have global warming, you have more and more catastrophic events, you have ice melting. The next speaker will talk a lot about the sea level rise and the consequences for coastal zones and so on. Hypoxia, salinity change, and another one is ocean acidification, and that's something that I work a lot on. Acidification was kind of the last one to be identified, and it's a direct consequence of carbon dioxide emissions. So basically, if you put more carbon dioxide into the atmosphere, about 1/3 of this carbon dioxide is absorbed by the ocean, which is great because it's already a mitigation, it's already limiting the negative effect. But it's not without consequences, because if you mix carbon dioxide with water, it turns into carbonic acid with cascading consequences for the chemistry of the water, and basically it makes the ocean more acidic. And that's something that we can observe all around the world. So that's a classic graph that has been built in Mauna Loa in Hawaii, where they've been monitoring CO2 for quite a while. And you can see on the red dots that you have this constant increase in carbon dioxide into the atmosphere. And then the yellow points is the associated increase in carbon dioxide into the sea. And the blue dots is the associated decrease in pH as a consequence of this incorporation of carbon dioxide. So basically, the ocean is getting more acidic, the ocean is getting warmer, and you have all these other consequences of climate change. And what is really worrying about this is that it's happening extremely fast. So this is another graph where you have a different time scale. This is 25 million years. And that's a reconstruction of the pH in the ocean. And what you can see is that the pH in the ocean on average is quite stable. And what you can see, the abrupt change you see on the right-hand side is what we are doing. So we are changing the pH of the ocean extremely fast, faster than anything that happened in the last 20 million years. And because of that, scientists are really worried, because it's predicted that if we keep burning carbon dioxide as we do, fossil fuel and increase carbon dioxide as we do, the ocean will be 2 times more acidic by the end of the century. So if you make a first stop here, we know that as a consequence of the growing population and consumption rate we have today, humans are changing the ocean at the global scale. It's getting more acidic, warmer, we have sea level rise and so on. The next question, of course, is like, does it matter? And unfortunately, the answer is yes. The last time that something like that happened on Earth, it was at the end of the Permian. And at the end of the Permian, it was one of the massive extinction in the ocean. So a lot of species just died off. And it's been estimated that 92% of all the marine species disappeared as a consequence of a large climate change event at the time. But of course, I'm not saying that because it happened before, it will happen today, but we have also other lines of evidence showing that these changes that I've been mentioning, global warming, climate change, ocean acidification, and so on, will have consequence for the species we have around today. So for example, this is an experiment we've done here in my lab a few years ago, and we basically compare the impact of acidification on the species you see here. It's called a brittle star. It's a very important species in the North Atlantic. So it's a keystone species creating habitat. And basically, if that species is gone, hundreds of other species will suffer from it. And what we did is that we cultured their larvae into water at the pH that you have today. And in water at pH that you can expect within a few decades. So that's 8.1 for today and 7.9 for the pH in the future. And what you can see is that you have a beautiful larvae on the top part at 8.1, but if you expose them to conditions that you can really expect really soon in a few decades, they just can't make a single larvae and they all die. So there is a potential here for species extinction within a few decades, so during our lifetime. And even worse, it's not only something we predict for the future, it's already having an impact today. And that's the story I will tell you a little bit later. It's about oyster aquaculture on the west coast of the US, where as a consequence of climate change and ocean acidification, oyster farmers were totally unable to keep their business. And the things collapsed. And then we will see that thanks to science and adaptation, now they are back into business. So in a nutshell, things are changing at the global scale as a consequence of our carbon dioxide emission. And we know as a fact that this will have consequences for marine life. So there will be negative effect on marine species, marine ecosystem, and all the services that are linked to us. So that will have negative impact on us too. So what can we expect really in the future? The thing is that the future will depend a little bit on what we do today. And that's why it's really important to act as soon as we can. The faster we're going to act, the better. And we can act in different ways. But if we want to summarize the options we have, it would be a little bit like this. So we are the little mouse on the right, and climate change is the cat, basically. And the situation is, if you face a situation like that, you have three options. You have doing nothing and wait to see what's going to happen, which is a terrible idea. Or you can either escape, which in our climate change story will be adaptation, or kill the cat, which will like get rid of the problem, which is mitigation. Mitigation being like get rid of the problem. And when it comes to carbon dioxide emissions, the mitigation option we have is basically stop producing carbon dioxide or removing the carbon dioxide that is already into the atmosphere. And that's a global challenge. We know that is something that we need to do at the global scale. So we have to have a coordinated action all around the world. And to do that, at the end, what we want is to decrease the carbon dioxide into the atmosphere. And to do that, we need to convince policymakers and people that change is needed. So basically, to do that, any kind of data that is showing that there will be negative consequences work. And we have tons of those data. So we don't need more science for that. We are virtually certain that there will be dramatic consequences for the ocean and for us if we don't change our ways, if we don't cut our carbon dioxide emission. So we know what the problem is, but it's not happening as fast as it should be. So the mitigation, which is decreased carbon dioxide, is not happening as fast as it should be. We keep producing carbon dioxide at an alarming rate today. So we need to change better. We need to change faster. And to do that, there will be a need of changing society as it is. So we need all to change, individuals, the way we consume and so on. And to do that, we also need strong policy action. The thing is that none of that will happen if these things are not in tune. For example, if you have strong policy action like a carbon tax, if people are not ready for it, it's not going to happen. And that's what happened in France during the Gilets jaunes movement, where actually policies decided, okay, we're going to put a tax on fuel, which is not a bad idea in principle, but people were not ready, they didn't understand, and it was revolution. So to induce this change, we need a combination of change in policy and understanding of citizens. And to do that, we need a specific kind of information. We need a better science communication. And to do that, I've been really inspired by this guy called Ken Caldeira. He's a researcher in Stanford, and he said, people have to sacrifice a little bit of their short-term self-interest to help the world be a better place for the long term. And how you get people to do that is the most important research that can be done. And that really inspired me into changing the way we think science. Because at the time, what we do, we produce science that is in something called the zone of complexity. So you have these two axes. On one side, you have the science uncertainty. So science is often complicated and uncertain. And then you have the societal values. It means like how much people will relate to the science we do. So most of the science we do is complicated and on things that nobody cares about. So if you want to use that to convince people that they need to change, it's really inefficient. So we argue that we have to move into the consensus zone, which is science that has strong societal value, that will speak to people, and that is easier to understand. And to do that, we made an experiment in my lab where we cultured seafood. So we know that in Sweden, people are crazy about these shrimps. So it's the northern shrimp. And we know that everybody loves it, everybody eats it. So if we can show that climate change or ocean acidification will have negative effect on them, we know that people will listen. So we decided, let's do an experiment on that particular seafood and see if acidification has a negative effect. And the answer is yes. If you expose shrimp to scenario you can expect in the next 50 years, the taste change and people can actually taste the difference. And we thought this is an amazing communication opportunity, because instead of just talking about the future, what can happen, or that the ecosystem will change and so on, we can make people physically understand what's going to happen, physically experience what's happening, and hopefully that will make them more willing to change. And to test this idea, we did tasting. So we went into public places and have a shrimp tasting and have people taste either like shrimps of today that they are used to or shrimp of the future. And most of the time, in 90% of the case, people can taste the difference. And so they taste both, and then they taste the future one, say, what's wrong with those ones? And say, well, these ones, that's the shrimp you're going to have in the future if you keep produce carbon dioxide as you do. So if we want to keep the quality of this seafood that you really care about, we need drastic change. And then we give them options. These are the few things you can do in your everyday life that really makes a difference. And we realized that by using that strategy, by making them physically experiencing something that is abstract, like ocean acidification, they are much more willing to change. And we follow them through time and realize that actually they are implementing change in their everyday life. Some becomes vegetarian, some travel smarter, and so on and so on. So in a way, we have enough science today to argue that a change is needed, but not all science will actually drive change in society. So that's why some scientists now should develop some better scientific strategies to do science that speak more to the people. So increase the efficiency of science communication. So that's the one side of what we can do today to avoid to have problems. It's like basically get rid of the cat. It's decrease carbon dioxide emission by making people understand that a change is needed and they can actually have an impact. But the thing is that that's going to take time. These kind of changes in society, in policy, might take decades, and we know that. And in the meantime, people that are depending on the ocean will suffer. And that's where the other side of what we can do is really important, the adaptation side. We can change the way we do things to make the ecosystem, the sea more resilient and be able to cope with more of the stress. So basically delay the negative impact of climate change and ocean acidification. Because on the picture here, you have an example of people that are highly depending on the sea. These guys are oyster farmers in Hong Kong, and all their livelihood depend on producing this one species of oyster. And they are suffering a lot from human activity. And very soon they won't be able to sell their product because as a consequence of the negative effect of climate change or pollution and so on. So if we want to help these people, we can't wait for society to change. We have to go there and find options for them. So basically it's a completely different scale. It's still a global problem, but with local challenges. When you want to help these people, you have to have local options. You need to go there and see what can we do to help them. And the options we have when it comes to adaptation are, we have a bunch of different options. And we're gonna have like 2 talks later about how we can do that in the context of sea level rise and build changing infrastructure and so on. And we'll talk now about 2 others, which is change practices for industries and assisted evolution, which is take advantage of evolution to find solutions. But there are many other things that can be done. For example, protecting some areas in the ocean, make them more resilient, is a great way of improving their capacity to cope with stress. Or reduce other environmental stressors is always a good thing. So there are a bunch of different options that are out there. And I just will give you one example here, which is the case study that I mentioned before about the oyster aquaculture in the United States. So as in 2007, what happened is that most of the oyster producer on the west coast of the US couldn't produce the little spat that they needed. So the way they work is they go in the field, they collect oysters, they reproduce them in the lab, and then when they have a mini baby oyster, they transplant them in cages outside, let them grow, and when they are big enough, they can sell them. So that's basically how it works. But that year, they were trying to reproduce them in the lab, but with no success whatsoever. So all the larvae were dying. And these things happen sometimes locally when you have a disease or something like that. But that year, it was really a generalized problem. It was all along the coast, and they couldn't identify the problem. So there was a big issues over there because a lot of money was on the balance. And then the first step was identifying the problem. And that's where science was really important. And the scientist called Dick Feely that you see on the picture here from the University of Washington went on the field, talked to the farmers, made measurements, and realized that the cause of this was ocean acidification. So the water was too acidic for the oyster to survive. And they identified, okay, acidification, we know what it is. It's a consequence of carbon dioxide emission. And they identified even the source. These you can see here, the main companies that are, most of them oil companies, that are responsible for this. But then the option seems obvious. We need to decrease carbon dioxide emission, but it's not that easy because again, that's going to take decades to do that. So the mitigation, this is what we should do, will take too much time. And that means that these oyster farmer will be without a job for a really long time. So to find another solution, they made some noise. So they make a huge stories where they basically show to the world, okay, we have a problem, oysters are dying, jobs are at stake and so on. And that drove a policy response. So policymakers went to the field. You have here the governor of Oregon, I think, talking to Bill Dewey, who is an oyster farmer, and he explained the problem to her. And the good stuff is that there was a policy response. So they realized, okay, there is a problem. We know what it is. These guys are in trouble. So what can we do? So they realized very early on that mitigation won't work because it's inefficient. It's going to work, but too late. And in the meantime, these guys will be out of business. So they say, what can we do else? What kind of adaptation strategy can we implement? And again, science came to the rescue. So what happened is that scientists started to study what is the impact of ocean acidification on oyster over their whole life cycles. And then they realized that actually oyster can cope with acidification most of the time. There is just one period in their life cycle where they are extremely sensitive, and that's the only 15 hours period between the trophophore stage and the D-shaped stage. So this really short period in their whole life where in that case, they are super sensitive to acidification. And they are sensitive because that's the period where they build their shell. When it's done, they are kind of okay. So that was a great discovery because then scientists came to the hatcheries and say, okay, if you change the way you do things and instead of keeping your larvae into this open water system as you do today, but for that critical period of 15 hours, you actually keep them in really controlled seawater, things will be fine. And that's what they started to do, and it worked. The beauty of that is that they started to implementing this change in practice. They adapted, so the industry adapted, and they are now back in business. The thing is that is really important is that it worked, but it's not going to work forever because even if they keep working as they do now, if we keep producing carbon dioxide, at some point, that's not going to work anymore because the oyster will reach another physiological tipping point and they will collapse. So that's an option to buy some time, not to solve the problem. So that's the important difference between adaptation and mitigation. Mitigation is really solving the problem. Adaptation is buying some time, like in the case here, but that doesn't mean that we have to ignore carbon dioxide emission and just don't do anything about it. It's really important that adaptation and mitigation works hands in hand. And there was a really cool paper in Science a few years ago where they basically said, if you don't mitigate, adaptation won't work. As simple as that. So we need to do both today, and we have to start as soon as possible. And to finish, I just wanted to say that we are now entering a really exciting time when it comes to ocean science. So the UN, the United Nations, started the process of what will be the UN decade for ocean science. And the idea is that for the next 10 years, starting in 2021, there will be a major interest in developing the science we need to have a healthy ocean in the future. And to do that efficiently, we will have to really identify what are the main priorities. Because as you heard many times, I'm sure, from Greta Thunberg and many other activists, our house is on fire. And when your house is on fire, you don't have the time to do whatever you want. You have to fix it as fast as possible. So the science of the future will have to focus on adaptation and mitigation and produce the information we need to change people's minds, change the way we do things, reduce carbon dioxide emission, and implement adaptation solutions for industries, for cities, and so on. So it's a huge challenge, and it's easy to be discouraged when you have a challenge that size, but I want to be optimistic and think that within the next 10 years, we're going to have major achievement in ocean science and ocean policy that will lead to a more healthy ocean. And the other day I was watching a documentary and I heard this speech that Kennedy gave about the space exploration, and he said we choose to go to the moon. And there is this really nice speech about they do that because it's hard, because it's a huge challenge, and that we can make it. And then I realized if we just change a few words in that speech, it's extremely valid today. And I want to read it to you to finish and say that if we choose to protect the oceans in this decade and do the other things, not because they are easy, but because they are hard, because that goal will serve to organize and measure the best of our energies and skills, because that challenge is one that we are willing to accept, what we are unwilling to postpone, and what we intend to win, and the others too. So basically, this is what we need to achieve. We are entering now into a new decade where we can put our scientific skills at the service of society and develop the science that we need to avoid all these catastrophic events that are in front of us if we don't do anything. So I'm going to finish here and say thank you very much to everybody for attending this. Thank you for your passion for the ocean and the work that you do, I'm sure, on every day. And I'm looking forward for your question at the end of the session.
Okay, thanks very much. And let's now invite Georg Unkieser to tell us about all the exciting things that happen in Venice Lagoon and Venice.
Thank you very much for inviting me to give this talk about the future of Venice and the climate change. I'm a researcher at the Institute of Marine Sciences in Venice. And for a very long time, I was working on the Venice Lagoon. I'm doing numerical modeling in order to see what the effects of climate change, what the effects of storm surge are on the Venice Lagoon. So Venice is flooded. Well, 10 to 20 times a year. It depends what you consider flooding. Clearly, the St. Mark's Square is the lowest part of Venice, and it is flooded basically at every spring tide. Not as bad as you can see it here, but basically a little bit more romantically, as you can see it in the upper left image of the slide. And when there is flooding, well, life is still going on. People cannot just say, okay, now we take a break for the next 4 or 5 hours. People have to work. People have to get to work. People working in the hotels and in the bars, they have to get to work, and so this is always going on. You can fight against the high water, against the acqua alta, how we call it here, with pumps or with trying to lock out the water from the shops. You can also adapt to it, as a lot of people that live in Venice do. You just go to your bar and drink your cappuccino and stand with the feet in the water. Well, acqua alta is a phenomenon that happens. Well, here you see it's like 5 to 6, maybe 10 times more than 110 centimeters per year. And what does this mean? 110 centimeters, that means that the St. Mark's Square will be in some parts already something like 30 centimeters underwater. Now, 110 centimeters is a very important level and a very important datum, because in the last decades, the pavements have been raised to basically 110 centimeters. So below 110 centimeters, water basically does not flood the city. Only 5% are flooded. But if you go over 110 centimeters, then they have a steep curve, and you can see that, for example, at 140 centimeters, there's already 2/3 of the whole area of Venice flooded. I show you some events that were dramatic. This was the high water event of 1966, the highest event ever measured, 194 centimeters. And this was a very dramatic point, because basically we didn't have any forecast for this, and people were completely unprepared for this. We had 2 years ago, the 29th of October, we had a storm, and it's called, it was the Vaya storm, it was called. It brought high water to the Venice Lagoon, but even worse, it basically killed big parts of the forests in the Alps, because of the channeling of the winds that were going over 200 kilometers an hour in certain parts, and this wind fell these logs, and these logs then finished into the waterways, into the reservoirs, and that's this brown stuff you can see. These are all logs that have been basically eradicated from the tree. Now we come to the 12th of November, which is just some months ago. And during daytime, there was, we could not foresee, we had no indication that it could become so worse that in the evening of the 12th of November, we had 189 centimeters. I'm doing water level forecast, and our forecast was something like 145 centimeters. So we were basically 45 centimeters off the real number. And this was something we now know we have to work on it, because clearly also in this case, a lot of people have been found unprepared. Because you see, if I say 140, 150 centimeters, people that have shops where their stuff gets wet at 180 centimeters, they say, okay, my stuff is safe, I don't have to do anything with it. If I warn them and I say it could be 108 centimeters, these people, they take the merchandise and they put it higher up. They couldn't do it because the forecast was not good enough. And this is the day after. There was a terrible storm. You can see basically it ruined walls and everything, and even it took the boats and it put the boats up onto the pedestrian walks. And this is a very interesting thing, because you can see there's a this boat has publicity on it. It's a biennale, which is the main art exhibition, and I would give a name to this picture, and it is this picture. This boat is not an installation. It is real life. What happened? Well, we had an extremely low pressure system that created these strong winds, Scirocco winds, that were basically pushing the water up to the north. And you can see there is even an extremely strong dip of pressure just going over the Venice Lagoon. And this was something like a medicane. We call this a medicane. It's not a hurricane, it's a medicane that forms in the Mediterranean. Normally we don't have hurricanes, but sometimes they form, and we had this situation. And this clearly is very difficult to forecast for the atmospheric models, and also clearly then using the data from the atmospheric models to forecast this, to forecast the aqualta, the high water, and the storm surge. And what you can also see is the green, the blue curve is basically the average of the monthly mean sea level. And you see in November, we normally have a higher sea levels, like 8 centimeters on average higher. In 2019, we had 32 centimeters higher water level for the whole November. We never had this before. And clearly, if you have this high water level, then it just takes some wind and some storm in order to create this high water. Well, what can we do? Now we have these interventions with the mobile barriers. The mobile barriers are being built, are nearly finished now at the inlets of the lagoon. So you build at these 3 inlets, you build 3 barriers that can then be raised if there is the danger of high water. And it's called the MOSE. It's called the MOSE project. And the first time it has been raised was in 2014. They just raised one of the 4 barriers that have been done. And just some days ago, 5 days ago, the 10th of July, oh, sorry, it's not 2014, I was wrong, 2020, just 5 days ago, for the first time, all the barriers have been raised. And basically, for the first time, the Venice Lagoon has been isolated from the Adriatic Sea. And this was the first time it happened. And it is only now 1 year away from being these barriers also operational. How do they work? Basically, they stay normally in normal operations, they stay on the floor, on the sea floor. And if you need to raise them, you pump air into them, and so they get lighter, and then they come up, and then they block the water from coming into the lagoon. If everything goes well, it's perfect. There are some problems. For example, one of the problems is that these elements are all the time underwater. And if they're all the time underwater, you can believe what happens. There will be rusting, there will be biofouling, there will be sediment that will be filling up these allotments. And so basically, one of the risks is that once you can raise them maybe, but then if you want to lower them, the places where it should normally go into it are full with sediments. And so these are all engineeristic problems. Hopefully they will solve these problems. Can the mobile barriers protect Venice? Yes, they can protect Venice, especially, let's say, if at the 12th of November, the MOSE would have been already operational, they would have, the barriers would have been perfectly able to protect Venice from flooding. However, during climate change, there will be other problems, and these will interfere with the operations of the MOSE. And this is my main talk, what happens during climate change with the MOSE, with Venice. What will be the future of Venice? Well, you see, this is a picture of the last 150 years. Certainly flooding will happen more often. The red curve is the mean water level. Every year you can compute a mean, and you can see it's rising. It's rising all the time. And we are now about 35 centimeters higher than 150 years ago. So Venice lost 35 centimeters. And the blue histogram, it shows how often we have high water. You see, this is high water is defined here as over 110 centimeters. Again, this 110 centimeters because the pavements are raised to 110 centimeters. And basically, that also gives you the level where the MOSE, where the mobile barriers have to act. Below 110 centimeters, you don't have to do anything. Above 110 centimeters, you have to close the MOSE barriers. And you can see in the last year, in 2019, sorry, because 2020 is not finished, we had over 20 times water level that was higher than 110 centimeters. Well, frequency of the extreme events, normally, as I told you, we have something like 5 to 6 times a year on average over 110 centimeters. But the exceptional high water is really the high water that makes a lot of damage to Venice. And before 2018, in 150 years of history and of measurements, we only had 18 of these events. And in the last 2 years, we had 6 exceptional events. So 25% of all the exceptional high waters happened in the last 2 years. And you can see something is happening. This is probably climate change. Well, you can also do, I'm a modeler, I'm applying models to the Venice Lagoon. And so, for example, you can see how often you have to close in order, if you have 10 centimeter sea level rise, 20 centimeter sea level rise, you can play around with it. Just focus on the 50 centimeter of sea level rise. 50 centimeter of sea level rise is now a very probable number that we could reach in 2100 at the end of the century. It's probably it will be even more, but let's say 50 centimeters. So you have two curves. It's basically, it gives you the uncertainty. And you can see there is at 50 centimeters of sea level rise, you have to close the Mose barriers between 300 and 400 times a year. What does that mean? Well, I have to remember you that the year only has 365 days. That means we will have to close the mobile barriers once a day, which is terrible. The mosaic was not done for this kind of thing. And you can also compute how long you have to close them. So not only how often, but how long, because normally if you close after 4 hours, you open them up. But if you have something between 70 and 80 centimeters of sea level rise, you get close to the level of 4,400 hours per year, and the year only has 8,800 hours. What does that mean? Higher than this, we will not talk anymore about closure of the lagoon, we will talk about the opening of the lagoon, because then the lagoon will be more closed than opened. What does it mean, safe in Venice? Because people were always when you discuss with people, they say, oh, we have to save Venice, but you have to be more precise. For people living in Venice, and that always happened, saving Venice is saving the city and saving the lagoon. It is a whole thing. They do not distinguish between each other. However, the sea level rise, this relation might come to an end. Venice was always living from its lagoon. It was, I mean, Venice for 1,000 years was a republic, was never conquered. Why? Because it had its center in a lagoon where you could not come neither from the mainland nor from the sea, because with these big boats, you could not go through the lagoon, you see. So Venice was safe. Now, at a certain point, you come to a place, a situation where basically this unity between the city of Venice and the lagoon of Venice might come to an end. And then you will have to choose. You have to choose, what are you going to save, the city or the lagoon? And I have to remember you, it's not a question if this happens, it's a question when this happens. We are basically nearly sure that we will have a sea level rise that will exceed 50 centimeters. If it is not in 2100, it will be later, but we will get to this. So when does this happen? We don't know. And the only thing I can see is, because there's not many other options you have, the only thing I can see is, in this case, you have to sacrifice the lagoon and you have to close the lagoon and have to change the ecosystem. You have to change the setting of the lagoon in order to save the city of Venice. And you will, in this case, basically create a freshwater lake. It is, to my opinion, the only way that in the long run we can save Venice. Well, if you want to make a freshwater lake, if you want to close the lagoon, if you have, not if you want, nobody wants to close the lagoon, but you have to close the lagoon, you have to have 3 points: no pollution, a good sewage system, and the industrial and touristic port should be transferred out of the lagoon. And just look at some examples of freshwater lagoons. You can look at the Danube Delta, you can look at Baltic lagoons. They're very nice places to live. The long or the short run, well, people say, well, it's right. Do we only have to look at the long run? No, we also have to look at the short run. And I think the MOSE will still be useful in the short run in order to buy some time, in order to get more options, maybe. Just look at what Keynes said. He was not an oceanographer, but he was talking about oceanography, and he's an economist. In the long run, we are all dead. Yeah, we cannot just think about the long run. We also have to think about the short run. What can we do right now with this? And just to remember you that Venice is not one of the worst, not in one of the worst situations. Venice can react. Venice has the possibility, has the funds to do something against the sea level rise. There are other countries that will not be able to do this. And I pick out just one of these countries, it's Bangladesh. With 1 meter of sea level rise, they will lose 17% of all the country they have. So you see, there's certainly countries that are worse off with sea level rise. And I come to my end, just one point. Now we had this COVID, and we had some, maybe you saw this also in the newspaper, that channels were getting cleaner and everything. Yes, we had this effect. And it could seem that climate change and this COVID emergency are the same. No, they're not the same, because the COVID-19 decreased tourists and boat traffic, and that's why we had clean water again. However, we could do this also by regulating touristic pressure and boat traffic. But what we cannot do is we cannot fight on a local level against climate change. And my last slide is this one. It's about emergency governance. You see, you have on the x-axis, you have the likelihood, the probability, and on the y-axis, you have the impact of certain emergencies. And you see the worst part is high likelihood and strong impact. And if you look at these things, it's all about environmental problems. It's all about environmental problems, because also water crisis, for example, it's colored differently, but it's also about environment. Yeah. So that's what we are facing. We face emergencies due to climate change, due to extreme weather conditions, natural disasters, and so on and so on. And you might now want to know, well, where is the coronavirus? Where is the COVID? Well, this is what is the environmental emergency. Here we have the COVID. You can see low likelihood and medium impact. And this were not people were not environmental people that were doing this report. This was the World Economic Forum. They completely missed this point, that the spread of infectious diseases could have also strong impact on the economy. And I'm sure in the next report they will do, they will place this kind of threat much higher up for likelihood and also for impact. And with this, I'm finished. Thank you.
Thank you so much, Georg. Your last slide is, of course, will lead to a lot of discussion. Yeah. But I would agree with you that it's not unrealistic. I mean, we can die of COVID, but if we all drown due to flooding, COVID is not an issue anymore. Yeah. So we have to put that all in perspective. It all has to do with how, as human beings, we look at the risks we run. And I thank you very much for sharing your insights in Venice Lagoon issues. I also appreciate very much that you put it in the international perspective. And I'm sure Kevin will do the very same. And so may I invite you, Kevin, to give your presentation. Thank you so much.
Thank you, Professor Stive. Okay, let me share my screen. Okay, it's a great pleasure to be here to meet with more than 100 professors, students, and scientists through this webinar. So I'm very pleased to be here to share with you about some recent progress on the research of the Mississippi Delta. So the title of my presentation is "What's the Future of Mississippi Delta Under Climate Change and Land Loss?" So in my today's presentation, I will talk about global sea level briefly at the beginning, and then I will talk about the land loss problem in coastal Louisiana. In particular, I will talk about the subsidence problem, which is a major issue here in southern Louisiana. After that, I will talk about lots of coastal protection and restoration methods being used in Louisiana. In particular, I want to talk about sediment diversion, which is a very useful and efficient method to restore the land, but it's also probably the most controversial method being used in the northern Gulf of Mexico. At the end, I will talk about some mitigation and adaptation method. Okay, I want to begin with this figure from IPCC. So in 2019, IPCC published a special report entitled Sea Level Rise and Implication for Low-Lying Island, Coast, and Community. So in this figure, you can see the prediction of the sea level under different kind of scenarios. So basically, the blue area is the scenario in which we have relatively slow global warming and more gradual sea level rise, whereas in the more pink and reddish zone, this would be in a scenario with much quicker warming and rapid sea level rise. So regardless of what's going to happen over the next 300 of years, the sea level will rise somewhere between half meter to maybe up to 5 meters. So this is actually a huge range. Okay, we are talking about meters. So it's a huge range going from nearly about slightly more than half meter up to 5 meter with lots of uncertainties. So this is the global sea level situation, which is impacting all the major coastal areas around the world. And now let's take a look at the land loss problem in coastal Louisiana. So I would like to acknowledge some early work done by U.S. Geological Survey. So this is the so-called red map published by USGS. All the red area indicate rapid land loss from 1932 to 2000. And if you look at the spatial scale, in southern Louisiana, we have lost a huge amount of area over those 70 years from 1932 to 2000. So what's going to happen? Lots of people have been predicting the land change in the next 50 years. In Louisiana, we have an agency, it's a government agency called CPRA, Coastal Protection and Restoration Authority. So CPRA has been publishing a master plan, and it has been updating this plan every 5 or 6 years. So here I have two maps to show the predicted land change over the next 50 years. And this map was published in 2012. So basically we are looking at the scenarios between 2012 and 2062. So there are two scenarios. The moderate one is like the situation in which we have moderate sea level change, whereas the less optimistic one would indicate a much faster sea level rise. So if you look at the bottom map, you can actually see a massive red area in which we will lose land to the sea. In Louisiana, we have not only global sea level rise, but also subsidence. I'm not sure if you know this, but geologically, southern Louisiana is actually the youngest land in the entire continental United States, okay? Lots of those land was built over the past 7,000 years, mainly the middle and late Holocene period. And because of that, the sediment is very new, and there have been lots of consolidation and dewatering process. On top of that, we have oxidation of organic matter, fault slips, together with other factors. And because of that, we have a huge subsidence rate changing from 6 to 12 millimeter per year. Here we have a map generated by Nihas et al. 2017. And you can definitely see very strong spatial variation over the entire southern Louisiana. But we have to deal with a very fast subsidence rate, and this is a huge problem here. So to better explain what's going on, I want to use this diagram. So let's ignore the red line for now. So if you just look at the blue lines, and this is a 2D short perpendicular transect. So this is the topographic profile. Here is the initial sea level. And then with some kind of rapid subsidence and a global sea level rise, you would have a situation in the red curve. So this would be the new topographic profile. This would be the new sea level. And now let's compare those numbers. So we already know that over the past 100 years, the global average sea level rise rate is about 1 to 2 millimeter per year. But in Louisiana, we have to deal with 6 to 12 millimeter per year of subsidence. So if you add those two up, you will have to deal with a huge local relative sea level problem. So in other words, in Louisiana, we mainly deal with the subsidence because subsidence is somewhere between 5 to 10 times the global sea level rise. And here I want to share with you a paper published in 2009. This paper was published on Nature Geoscience, led by Michael Bloom and Harry Roberts. So the title of the paper was Drowning of Mississippi Delta Due to Insufficient Sediment Supply and the Global Sea Level Rise. So I don't want to go over all the details, but I want to draw attention to the last sentence in the abstract. So look here. We conclude that significant drowning is inevitable even if sediment load are restored, because sea level is now rising at least 3 times faster than during delta plan construction. So this is actually a very well-received paper, many citations, and lots of people cited this paper because this is kind of a learning signal to not only our scientists, the professors, the students, but also the policymakers and managers. And in that paper, Bloom and Roberts also generated a map to show the flooding area in southern Louisiana. And this map is somewhat scary and very alarming, because if you take a look, pretty much everywhere in the southeastern part of Louisiana will become water. And then New Orleans will be kind of isolated from the mainland. Baton Rouge is over here. But keep in mind, in this prediction, Bloom and Roberts assume that the sea level rise will be about 1 meter over the next 100 years. But you already saw the new curve predicted by IPCC. In some scenarios, the sea level rise might be more than 1 meter over 100 years. Also in this model, they did not include sediment input. They did not include catastrophic events such as hurricanes. So now let's move on to the master plan prepared by CPRA. So as I explained, Coastal Protection Restoration Authority in Louisiana has been updating a master plan for a sustainable coast. So every 5 to 6 years, they update the master plan. So here I have a front cover page of the master plan 2012. And then a new version was published in 2017. And now people are preparing the newer version, which will be published in 2023. In this plan, many projects were proposed. So here I just list the major type of project. For example, structural protection, which is in purple, and then marsh creation, which is in green, sediment diversion is in brown, among others. So if you deal with the coastal Louisiana, it's a super complex system. Over the past 7,000 years, the Mississippi River has been built a large deltic complex, okay? So we have the Mississippi Delta here. We have numerous barrier islands. which are very important to protect the coast and regulate the salinity. Then we have massive wetland area, which is in green. And those green areas actually are proposed future sites for man-made marsh creation. On top of that, you can also see those brown dots. Here is actually a large receiving basin for a sediment diversion. And on the eastern side, there's another large diversion. So I just want to give you an idea. So this is a small, well, a sizable estuary. It's called a Barretteria Bay in southern Louisiana. And CPRA is planning a large diversion. It's called a Mid-Barretteria Bay diversion. The cost of this single diversion is about 1.3 billion US dollar, which is probably the largest diversion project in the history of the United States. And now if we look at the budget, so the plan was to spend 1 billion US dollar per year over the next 50 years. So it's a 50-year, 50 billion ambitious project. In this project, there will be different kind of project types. The largest money portion will be spent mainly on marsh creation. About 20 billion will be on marsh creation. About 3.8 billion will be on sediment diversion. So those diamonds basically show the percentage of the money spent on those projects. But if you look at the land created by those projects, for sediment diversion, you only spend about 3.8 billion US dollars, but you would create a very large area, which is more than 300 square miles. So because of that, no question, it's clear that sediment diversion is the most efficient method to create new land. However, as I explained before, sediment diversion is also the most controversial project because lots of fishermen, lots of farmers are very, very concerned about the diversion because when you open a new cut on the river, you introduce fresh water, nutrient, sediment, and pollutant into the ambient bay, which may have lots of negative impact on the fishery, on the oyster, and others. So because of that, on one side, diversion can be very powerful to create land. On the other side, we have to be very careful about the negative impact. So how does it work? In this massive, ambitious master plan, there are lots of models will be used. So here is actually a framework published by Piani et al. 2003 to summarize the modeling effort in the master plan. Lots of models will be included in this plan, including ecohydrology, wetland and barrier morphology, vegetation, ecosystem, storm surge, risk assessment, among others. I don't want to go into the details, but you can actually figure out the scope and the complexity of the modeling work in this master plan. So regarding the sediment diversion in the master plan, there are several diversions planned along the Mississippi River side as well as Atchafalaya side. I mentioned the Mid-Barretteria Bay diversion, which is located over here, and this is the size of the diversion. The cost of this diversion is about 1.3 billion. Now, I want to introduce a recent paper. It's a review paper published on estuary, coast, and shelf sciences in 2019. I'm the lead author. I was collaborating with Dr. Sam Bentley, John Day from LSU, as well as Angelina Freeman from CPRA. So we reviewed about 170 papers to look at all the past physical and geological studies relevant to sediment diversion. And this is the key conceptual diagram we developed together. So when you have a large river, you open a cut. You divert water and sediment into a receiving basin. you start to build land, which is the Q subaerial, how much land you can gain. But sediment also deposited in the subaqueous part. Some sediment can escape the bay and deliver into the deeper part of the ocean, which is called the Q escape. So of course, we would like to maximize the sediment retention rate. In other words, if you get a 100 unit, you would prefer to retain 50 or 30%. The reality is that you normally just retain a very small percentage because lots of the sediment is mud. They are really, really small and fluffy, and they can be flushed out of the system. So how do we improve the sediment retention? There are different methods people have been using. One is the terracing structure. You can build those small parallel structure to break the receiving basin into smaller parts, and this will minimize the wave impact. You can also build a large elongated structure such as sediment retention enhancement device, which is called shred. If you are near the marsh, you definitely need to use some kind of a device to retain sediment near the marsh edge to minimize marsh edge erosion. For example, lots of wave dissipation device can be used. You can even use mats, meshes, or some man-made material to build a living shoreline to keep a healthy marsh. So regarding the sediment retention, we also did summarize the review, and what we found was that if you are very close to the ocean, if you are close to the coast, most likely you would experience strong tide and a wave. Because of that, the retention rate would be relatively low. By the way, the horizontal axis on this plot is river kilometer. Is actually the distance in kilometer upstream of a delta or estuary bay mouth. So if you deliver more sediment to a more landward area, most likely you would be able to trap more sediment, and you would lose less because of a smaller oceanographic process. So because of that, we were able to establish this semi-quantitative curve to inform policymakers that in this region, if you want to keep the land very close to the coast, most likely you have very, very small retention rate. This is not very efficient. Eventually, people will need to retreat, migrate landward, find some area to build a new land so that we can retain more sediment. Regarding the method we can use to do mitigation and adaptation, our recommendation is that in the future, we should focus on how to enhance river sediment delivery to the marsh or to the bay. How do we increase the sediment retention? How do we minimize the erosion near the barrier island, near the marsh edge? On top of that, in order to fully understand the system, we definitely need a better understanding of the geological framework. For example, a paleo river channel with lots of sand is definitely not very erodible. It must be very stable without much subsidence. Whereas if you are in a muddy interdistributary bay or a marsh with high organic matter, and if you are on top of a fault, most likely you will have huge subsidence and lots of erosion. So we definitely need to understand those underlying geological processes. Shred is a very promising method, and people have been using shred in West Bay, on Mississippi Delta. People have been using terrace in Terrebonne Bay, which is in southern Louisiana. They are proved to be very efficient way to retain sediment. In the future, I think we need to consider not only science, but also not only physical science, but also social science. So population dynamics is the key, and we need to advertise those coastal mitigation adaptation methods and make sure people are willing to move, people can cooperate. And a more landward sediment diversion would give us a higher retention rate. So what will be the future of Mississippi River Delta plan? I would like to use a very, very beautiful map generated by a competition team in Changing Course. So Changing Course is actually a large initiative to encourage the submission of new ideas of innovative method to save our coast. There were 3 winning teams. One team generated this beautiful map of southern Louisiana. New Orleans is here. If we divert lots of water and sediment to the ambient bay and marsh, Mississippi Delta will be destroyed. It will be converted from a bird delta to a barrier island and eventually to a submarine shoal. Unfortunately, we will lose the beautiful bird delta, but we will be able to create a new delta somewhere else. It will be very, very different. The morphology of the future Louisiana will be very different. Okay, that's all what I have. If you would like to know the details about the paper or the references I used in this presentation, feel free to search my name as you should be able to visit my college website and my lab website in which you can find all the publications. Thank you.
My question to Sam would be, would you address the points that you raised for discussion to Georg? Would you address the issue of not being able to close the lagoon? And to Gavin, I would like to ask, will you please have a little look at the questions that were sent to you and pick, you can't answer them all here in our discussion, but pick 1 or 2 that you think are worth to discuss in our community with the attendees. And so Sam, you're probably best prepared because you've had some time to reflect.
Thank you. I tried to answer all the questions that were directed to me, and I could see like basically 2 main topics. I think they were more like technical questions, but one was discussion about like the source of carbon dioxide. So basically how society and ourselves actually produce this carbon dioxide, and basically what kind of changes are kind of important. And the other one is more philosophical about like the role of science in driving change. And shall we do better science communicator? How can we influence policy and so on? So for the first one, I just wanted to give a few numbers because I think it's kind of fascinating. So most of the carbon dioxide is produced by fossil fuel today. That's one of the major source of burning fossil fuel. The second one would be deforestation, and then followed by industry, for example, cement production. But when it comes to us, like every citizen on Earth produces now about 4.9 tons of carbon per year. And basically, if we want to be sustainable in the future, we should go down to 2 tons or less, basically. So the challenge is quite big, especially in some countries where every citizen produces quite a bit. But then the interesting part is to break this into what are the sources for each individual. And actually the first source is energy on average. So the way we use energy for a car, and not for cars, it's the car part, but for warming our house, cooling our house and so on, that's 32%. The second one is basically transportation, which is 28%. So use of car, traveling by plane, and so on and so on. The third one will be consumption, like buying things, which is 26%, and then food is 14%. But it's kind of interesting to see, like, for example, just the fashion industry correspond to 10% of the emission. So that's one easy thing you can do. You don't need to buy new stuff all the time. You can just, recycle, repair. That's what I do. I barely buy things. My son yesterday said, "Oh, Dad, you never buy anything." And I think it's because we try to use as much as we can. And I think that's a good advice. That food is also a very important source. For example, producing 1 kilo of beef costs 60 kilos of CO2. Cheese would be 21 kilos. chocolate 19 kilos. So, you know, all the things we like basically produce of carbon dioxide. And in comparison, 1 kilo of peas is 0.9 kilo. So if you can move toward a more plant-based diet, that has a huge impact in terms of carbon dioxide emission. And if you like meat, eat meat. I think I'm 99% vegetarian, but sometimes we eat good meat, and we have a local producer that have sheep, and we go there sometimes just to, you know, it's okay. But if you can move, so that was one of the questions, how is becoming vegetarian a good thing? Is because your individual production change. Another thing that kids don't know is internet is a massive source of carbon dioxide emission. And actually, I was asking to my son the other day, like, what do you think is the worst, like eating a steak a week or spend 3 hours a day on the internet? And actually, it's the same thing. So we don't need to stream all the time. You know, we don't need to you know, and that's the thing. It's basically reducing consumption on anything. So everything we do has an imprint, and I talk about carbon dioxide, but it's true for pollutions and so on. So that's one of the way you can really reduce your impact, is get informed, find the numbers, they're out there, make your carbon footprint, talk to your policymakers, they all vote right. I mean, all these things can have a positive impact. And the second part was how to drive change, what is the role of scientists in communicating, and that's a really tricky question. Actually, I truly believe personally that change will come from policy, because it's such drastic change for society that we will need informed policy. We'll need like brave policymakers who's going to take decisions and enforce them. And you have a bunch of options out there. The thing is that it's not going to work except if people are willing to accept the change. And that's why it's really important as scientists to talk to everybody. You have to talk to every citizen you can. Go to school, go write in the press, go to internet, whatever you can, communicate it right, and communicate it positively. Like basically, just don't say we are in trouble, we're all gonna die, this is not working. But say, okay, we are in trouble, but there are options, and this is what you can do. And I have a lot of experience now talking to policymakers, and not all of them are evil like some people think. Actually, most of them are really trying to do the right thing. But if you come with problems, they don't like it. You have to come with options. And we talked a lot about options here today, and that's something that is really exciting. So I truly believe that communication is one of the key, that scientists can contribute to the change by communicating more efficiently and doing science that is more useful for society. So that was my 2 cents on some of the questions we had out there. If somebody has a more specific question for me, they can also shoot. I had some technical question about acidification, but I think that's answered in the chat.
Thanks very much, Sam. Thank you for your response. Georg,
Yes.
can you say something about that important question?
Well,
how is climate change impacting the water quality of the lagoon?
So, you know, the biggest problem in Venice is that there was, for a long time, there was no scientific discussion, because basically people didn't want to have the scientific discussion because industry wanted to build these mobile barriers. And this was a big problem. In 2011, there was an international conference sponsored by UNESCO, organized by UNESCO. And 3 weeks before this conference was going to take place, it was canceled. It was canceled because the Italian government intervened. They didn't want to have this, in this precise moment, this conference to be held. Why? Because it was on the future of Venice under climate change. It was basically my talk, you see? And if you do the future of climate change under and in the future of Venice under climate change, you have to talk about the MOSA. You have to talk about the mobile barriers. It's one of the most important things. And they didn't want to have any discussions on this. And so basically this conference, it was the only conference I ever know about that has been canceled 3 weeks before, and just because of political reasons, not because of the COVID or something else, you see. And I'm very much sure that we have to wait another year, a year and a half, because in 1.5 years, the MOSA will be operational. It will be finished. Everything has been built, and then we will be able to start a scientific discussion. Because only then people will feel that now we have everything we wanted, and now we can think about alternative problems. Like one of the alternative solutions could be, for example, Do we have to close the lagoon sooner or later? We don't have to close it in the short run. We might have to close it in the long run. And then we can discuss about the problem that what we have to do in order to be able to close the lagoon. And you see, there's 2 of the 3 points I showed, no pollution and sewage system. They're helpful for the lagoon. They're helpful anyway. You can do it anyway. It's not something you do and then you say, oh, I threw out my money. I wasted my money. No, it's helpful anyway. So we can start with this one. The 3rd point, taking the port out of the Venice lagoon, this will help sooner. This will happen sooner or later because if you have to close too often the lagoon, then the boats cannot go through anymore. And you just have to think about a cruise ship that has 3,000 passengers on board, and they arrive in Venice and the gates are closed and they have to wait for 4, 5, 6 hours. Yeah, this can happen once, this can happen twice, and then the cruise ship will say, okay, I go to Trieste, because it's much safer. I know that I can always go into the port of Trieste. In Venice, it's not sure. The port authority asked to have a reliable forecast for Venice for 48 hours. 48 hours. They would like to know for 48 hours in advance if the gates have to be closed or not. This is impossible. We will never be able to do this in the next 50 years. And why do they need to know this? Because 48 hours before, the ships that have to go into the port of Venice, they come into the Adriatic Sea at the Otranto Strait. And it takes them 2 days to travel up the Adriatic Sea, and then they want to be sure, once they do this, they want to be sure to be able to get into the Venice port. And if they're not sure, they say, okay, maybe we look for another port. So these are the problems. I think something can be done. We have to open a scientific discussion also with policymakers, but we have to avoid this, that somebody puts you into an angle and say, oh, this guy wants to close the lagoon. I don't want to close the lagoon. I'm very happy with the lagoon right now. But we also have to face the problem that sooner or later we will be constrained, we will be forced to do this step.
Thank you so much, Georg. Kevin, I saw a very interesting question for you.
Sure. Yeah, there are several really interesting questions in the box. So I would like to answer the one related to salt marsh, because wetland loss is the biggest issue here. So the question was, salt marshes are at great risk of being submerged by sea level rise. Is there even space for them to move back or move northward in Louisiana? Are there major projects to add new sediment, thin layer deposit to enable them to keep up better with the sea level? So, so I think for this question, if you talk about short term, the answer would be yes. CPRA has been doing sediment diversion, marsh creation. People have been pumping those sediment from the Mississippi River and deliver them tens of miles to the marsh surface to create a new land. So in the short term, yes, we do have space. We have loss of wetland lost. Over the past 30 to 50 years, we do have space to build new ones on top of it. But over short term, if we, over long term, excuse me, if you deal with much higher sea level rise, say the sea level rise is somewhere between 1 meter and 5 meter, and then pretty much the entire southern Louisiana will be underwater. Only a very limited area will be exposed. And those areas will be mainly on those old river channels, such as the Mississippi River Channel, Bayou Lafourche, or Atchafalaya River Channel. And in that kind of situation, pretty much everywhere will be water in southern Louisiana. And there's not much you can do. You probably have to retreat further up to the north. Thank you.
Okay. I see more and more questions coming in. I suppose we could go on for hours, but I don't think it's wise. I see slowly the number of participants going back to, at this moment, 90. I think we can all see our conference, our webinar back on YouTube. And I think it's been very useful. I want to thank both Sam, Georg, and Kevin for their amazing effort. And I'm sure we will have helped a lot of people to get good thoughts about what we can do. Thank you so much. Wish you all well, and we'll be in touch in future. Thank you.
Yes.
Thank you very much.
Thank you.
Thank you,
all the
Professor.
chairs and all the speakers.
Yeah, thank you, Anna.
Stay safe.
Yeah, many thanks to the water and DPI for organizing this. This is great. I really enjoyed it.
Thank you.